So now we're going to move into part 2 of our conversation about Bayes' theorem, where we're actually going to see the equation, and we're going to work with it a little bit. And so you can see you'll be able to see it's the same thing we did with our tree diagram, except it's a little bit more straightforward. It's a little faster, certainly. It's a little streamlined. So before we actually get into the equation, we have to go over a little bit of notation, how it looks. Okay, so let's go over these basic notation. Start with P always indicates probability. P always indicates probability. So P and then whatever's in the parentheses is what this is a probability of. So this is the probability of A, probability of something happen, probability that someone's a drug user or someone has a disease or someone is a terrorist or something like that. This little line right here, that's squiggle mark, which you can see on your keyboard is the squiggle mark right next to the 1. It's the same thing that, if you hit Control plus, so if you hit Control plus that apostrophe mark, that will, make you show formulas. The squiggle line right above that apostrophe mark, if you hit Shift and then that mark, that apostrophe mark, you get this squiggle line. That's this symbol right here, tilde. Anyway, so this tilde means not A, so the probability of not A. If you have two tildes together, not, that's just the same thing as A. So probability of A might be what is the chance if it's going to rain. Probability of not A is what's the chance of it not going to rain. By definition, probability of A plus the probability of not A is always 1. Okay, these are mutually exclusive and they are completely exhaustive. Something either will happen or it won't. So that's that basic idea. These two are conditional probabilities. That vertical line, which you can find if you press Shift plus slash. So at least most keyboards on mine, it's a vertical line, the button that is right above the Enter key. You can see it's a slash button, and then above that slash button, there'll be just like this vertical line here. That means conditional. So if you do A vertical line B, that's the probability of A given B. Probability of A assuming B happens. What's the probability of it raining versus what's the probability of it raining given it's the month of April or May? What's the probability of it raining given that it's the spring versus the probability of it raining? What's the probability of it raining given it's the winter? Okay. So you can see how once you start adding those conditions, you can naturally see the probability change. And then, of course, you can put that not symbol anywhere, so I just put it here just to indicate the probability given it's not B. Right. The probability of A happening given it's not the spring. Note that we can take that same idea, the probability of A plus the probability of not A equals 1. We can apply it here. The probability of A given B plus the probability of not A given B, that's going to all equal 1. The probability that it's going to rain given it's spring plus the probability that it's not going to rain given it's spring is 100%. It's either rain or it's not going to rain. That's 100% chance. Now you cannot do the same thing here. It would be false to say this. It would be false to say, what's the probability of A given B plus the probability of A given not B, that equals 1. No. The probability of it raining, assuming it's spring, plus the probability of it raining, assuming it's not spring, is not 100. It can be 1% over here, that, let's say 20% over here, assuming it's spring, and maybe only 10% over here, assuming it's not spring. That doesn't equal 1. This is not true. But this is true by definition. This could be true by coincidence, but it's not definitely true. It's not obviously true. So hopefully we got this down. Let's do Bayes' theorem. Bayes' theorem essentially operates off this idea that we should not assume just because the probability of A given B does not equal the probability of B given A. The probability that someone is rich just because they're a CEO does not equal the probability that someone is a CEO just because they're rich. The probability that you are rich, assuming you're a CEO, does not equal the probability that you are a CEO, assuming you are rich. Probability of A given B does not equal the probability of B given A. To understand the probability of A given B, we have to use the probability of B given A, but there's a lot more going on. So let's take it one step at a time. So we're trying to figure out what is the probability of A given B. This might be, what is the probability that, the previous example was the probability that someone is a drug user, assuming they test positive. What's the probability of someone being a drug user, assuming they test positive? Well, that is equal to the probability of them testing positive, assuming they're a drug user, times the chance that they're a drug user. This same numerator is copy and pasted down here. The probability that someone tests positive, assuming they're a drug user, times the chance that they are a drug user, plus the probability that they are a drug user, that they test positive, assuming they're not a drug user, times the chance that they are not a drug user. So note in here, these are two different ways to get to B. You can get to B, and in this example, you can get to B honestly, true positive, or you can get to B sort of by mistake, false positive. But these are two different ways to get to B. In fact, sometimes Bayes' theorem is abbreviated as just probability of B given A times the probability of A divided by the probability of B. But I wanted to map out for you exactly how we get to the probability of B. And that requires understanding there can be true positives or false positives. And I'm using that true false positive because that's the example we used, but you can swap out A and B for anything. You can make, what is the probability of someone being a drug user assuming they test negative? Just because they test negative, what's the chance I missed them? And then we would go through that math. So I'm going to do two examples so that we get a handle on the math, both for our drug user example. We will use 1% are users, 90% sensitive, and 80% specific, just like we did in our example from last video. Now, the easiest way I found to do this is to translate this equation into symbols, essentially, so that we can keep track what is specificity and what is sensitivity, what's 1 minus it, etc., etc. So first things first, I erased all the A's and B's. I could just write the same thing over again, but through the magic of editing, it looks like I did this really fast. Then I'm going to replace A and B with user and positive. Right? What is the chance that someone is a user, assuming they test positive for drugs? U is that they're a user of drugs, and positive test result. Well, that is the same thing as the chance that someone tests positive, assuming they are a user. Okay, these are not the same thing. Times the probability that they are a user. Chance that they test positive, assuming they are a user, times the chance they are a user. Chance they test positive, assuming they're not a user, times they're not a user. And then we can very carefully go through the math using this information. So let's start with this first one. What is the chance that someone is testing positive, assuming they are a user of drugs? Well, if you're assuming you're a user, that's a positive state. That means we look at sensitivity. If it's a positive state and they test positive, is that correct or incorrect? That's obviously correct. So we use 0.9. What's the chance that they are on drugs? Well, that's 1%. In the same story, chance that we get a positive result, assuming that they're a user, that's sensitivity, so same thing, same thing. And so it gets fun. What is the chance that they test positive, assuming they're not a user? Well, not a user sounds like specificity, right? Detecting a negative state. Can the test correctly put them in a negative state? Now, some people will say, okay, I'm looking at specificity, so I'm going to put in 0.8. Don't do that, because specificity is when you correctly identify, the percent chance you will correctly identify a non-user as a non-user. We didn't correctly identify a non-user as a non-user. We called the non-user a user, test positive, even though it should be negative. So the specificity is wrong. And since it can either be correct or incorrect, right or wrong, and we take 1 minus 0.8 to get 0.2. Since it can either be right or wrong, we take 1 minus 0.8 to get 0.2. And finally, not a user. Well, if 1% are users, then 99% are not users, so and then we simplify. So we have our 0.9 times 0.01 is going to be 0.009. 0.09 is the same thing here because it's the same thing. And then we do 0.2 times 0.99, which is going to be 0.918. 0.9 over 0.207, which is, of course, about 0.043 or 4.3%. If you're saying, well, that's the result we got last time in the last video. Yeah, that's the point. Note that what we did in the last video is exactly what we did here, except we didn't have to make a tree diagram, right? Our 0.009 is the same thing as before. This is the two different ways to get a positive result. And then we took one divided by the other, and we got that. I don't really care which way you do it. You can make the tree diagram, you can use Bayes' theorem, but it's important to understand that Bayes' theorem gets us there. It's important to know. For one, I think Bayes' theorem is faster, and two, it's easier to convey and justify, especially if you're doing this online. You can just type it in, type in the formula, type in the equation, you can get there. But it's also just important to understand what Bayes' theorem is doing and how it works. That's the whole point. That's the kit and caboodle. That's the purpose. Let's do another one. We got our Bayes' theorem right here. We have our critical information about the test. So users are at 1%, sensitivity is at 90%, specificity is at 80%. And then here's our blank Bayes' theorem. Now before we did, what is the chance of someone being on drugs, assuming the test comes back positive? And we learned our positive tests don't mean that much. What do our negative tests say? What are the chances that someone is not on drugs, assuming the test comes back negative? So what is someone not a user, assuming the test comes back negative? Now to do this, we have probability of A given B. We flip it to make probability of B given A. So we'll do the same thing here. Probability of someone not being a user, assuming the test comes back negative, becomes probability the test comes back negative, assuming they're not a user. Times the probability they're not a user. Of course, in the denominator, first part is exactly the same. In the other part of the denominator, it is still negative, but now it is not users. And the probability of not users. And I think for our own sanity, we can simplify both of those as just to be probability to get a negative result, assuming they're a user, probability of a user. So I'll erase that U, erase that not U and put in a U, erase that not U and put in a U. Because it's mathematically the same thing. It's identical. Okay, now let's throw in the numbers. What is the probability of someone getting a negative test result, assuming that they're not a user of drugs? Well, not a user We're assuming they're not a user. Is that sensitivity or specificity? That's right, specificity. And is the test right or wrong? Absolutely. The test is correct. It is negative, and it should be negative. They're not a user of drugs. So that specificity we're going to put right here. Times the chance that they are not a user. Well, something we talked about in the previous question. How likely are they not to be a user? Pretty high. All right, 1 minus this. Same thing, copied and pasted. And so now we took care of this part, we took care of this part, we need to do this last part. What is the chance of getting a negative test result, assuming they are a user of drugs? Well, again, now we're assuming they are a user rather than not a user. So now we switch from specificity to sensitivity. And is this test right or wrong? Exactly. It is wrong. So we'll do 1 minus sensitivity. And then chance that they're a user. Now, before we continue, I want to emphasize something to you. In both the first one we did, what is the chance that they are on drugs, assuming the test comes back positive, and what are the chances they are not on drugs, assuming the test comes back negative? In both of those examples, we looked at the raw value of either specificity or sensitivity, and then 1 minus the other one. We switched over and we did 1 minus the other one. And the big reason why we did that is because in both of our questions that we're asking, what is the probability that this person is on drugs, assuming it comes back positive? What is the probability they are not on drugs, assuming it comes back negative? And both those questions we're basically asking, is our test result correct? And so we start with the correct number, the probabilities of it being correct, which are either 0.9 or 0.8, and then we switch over to it being not correct. But it doesn't have to be that way. We could easily have asked a question, what's the probability of them being a user even though the test came back positive? What's the chance of them not being a user even though the test came back? What's the chance of them not being a user if the test comes back positive? What's the chance of them being a user even though the test comes back negative? And then it would be different over here. So just keep that in mind. Don't be mindless about this. Really have to think about each unit, each result, each component. That's why it's nice to map it out this way. You can see the parallel between these two. All right, well, now it's just doing some math. So note, of course, this is going to be 0.001. 0.1 times 0.01. This is 0.792. This is obviously 0.792, so 0.792 times, plus 0.001 is 0.793. So that's how this simplifies, which you can easily tell becomes something pretty high, or a 99.87% chance. A 99.87% chance. If the test comes back positive, they really are probably not a user of drugs. Note that we still have Bayesian updating. We got new information. We learned it's not a 100% chance. Right? It's obviously not a 100% chance because we could have missed someone. We could have gotten something wrong. So it's not a 100% chance. But it's not the same either. It's not still 99%. It's now 99.87%. It's higher, but not perfect. So this shouldn't surprise us either that we got this result. We got a very high result. We got a very high result because it's unlikely we'll encounter anyone who's actually a user of drugs, only 1% chance. And then on top of that, the test has to be wrong, which doesn't happen that often, 10% of the time. And so that makes up a very small percent of our negative test results. Right? We test 1,000 people. We would have 793 negative test results, and only one of those negative test results will be a false negative. The vast majority, 792 of them, will be a true negative. So in sum, Bayes' theorem reminds us that no test is completely accurate. Right? We take those accurate numbers in, we throw them in. We take those accuracy values, we throw them in, and you can see it's hard to test for some things, especially when those things are rare. That said, when the thing that we have is common, like in this case, there's lots of non-users of drugs, even then, our results are not perfect. They're certainly good enough, but in most cases, but they're not perfect, right? So it tells us how much to update our expectations. It not only tells us that we should update our expectations, but how much we should update them. And that idea that we're always thinking in terms of probabilities, of not perfect certainty, of, well, maybe there's an error, maybe there's a mistake. That's not just good thinking, that's also the essence of statistical thinking. Thanks.